Swayam Prabha. Digital India. Educated India.
I welcome you once again to this lecture of flow through porous media. What we were discussing in the last lecture was mass continuity. What we did so far is we tried to understand the flow through porous media through Darcy's law, through continuum assumptions, and through definitions of permeability and porosity. What we did next is we extended it to a mass continuity equation in 3 dimensions, and then we extended it to cylindrical coordinates, because in many cases beyond Cartesian coordinate you can leverage the symmetry in cylindrical geometry to simplify equations. So, cylindrical geometry we have considered, and we have arrived at some equation for the pressure profile and velocity. So, let us just recapitulate quickly the equations that we arrived at there. So, we were discussing about Darcy's law, mass continuity in Cartesian and cylindrical coordinates, and pressure equations. So, what we did in the last lecture was we arrived at this expression for VR. We arrived at this expression for VR, and we arrived at this expression for VR. We found that this VR is inversely proportional to R. That means, we saw that if this is the x axis is the radial distance from the center of the well. So, if this is radial distance and if y axis is velocity in radial direction, that means, if we are looking at let us say some radial distance r from the center, and if we are looking at since it is a radial flow, if we are looking at this radial flow, and if you are trying to find out how VR, the radial velocity, changes with distance from the center, we found that the absolute value of this velocity would be decreasing with r, because VR is proportional to 1 by r. Okay. So, depending on what is the sign on Q, if the well is producing, that means flow is out from the well, or if you are injecting something through this well. So, in that case this sign of the Q differs, and Q is considered positive if radial velocity is negative. That means, Q is positive if something is produced from the well, and this radial velocity is negative only if flow is opposite to the directions that are shown here. So, this we discussed in the last lecture, and how the pressure profile looks like under such situation. So, what we do next is we have found out the pressure profile in that case. What we do next is, now we look at non-uniform permeability. That means, where we have 2 strata with different permeability. 2 strata with different permeability. That means, up to certain radial distance we have permeability, let us say K1, and beyond this distance permeability is, let us say, K2. So, in one case it is K1, another case it is K2. So, in this case you have this, first of all we had this Laplace equation, right. When we had uniform permeability, we know that we have to solve this equation. Okay. So, it was in Cartesian coordinate, it was del square p del x square plus del square p del y square. If we are not considering the z direction, then this was supposed to be 0. That was the Laplace equation. Now, in case of radial coordinate, it was it was little different, but we have a very similar equation in terms of del p del r and del p del theta, and there basically we can call this equation as del square of p is equal to 0. That is basically the governing equation. Now, since you have two different strata, so you have to satisfy two different. So, we will call this part where the inside this cylinder where the permeability is K1, let us say all these pressure is a function of R. I call this P, I call this P1. This is a function of some function of R. Okay. Similarly, we have another pressure, another definition of a parameter, which is P2, which is applicable for the region outside this inner cylinder. So, that is the region where the pressure we call it P within bracket 2. So, we instead of 1 P, now we have P1 and P2. They are function of R, and they have their own ways to explain things. So, basically now we have to satisfy del square, now we have to satisfy Laplace equation for P1 and Laplace equation for P2. These are to be satisfied separately. Okay. So, now we have two different equations, one for the inner strata and the other is for the outer strata. And further, when you write two equations, they are to be coupled in a sense at the surface of discontinuity. That means, this is the surface of discontinuity, that means, this is the surface where you expect this is the surface where you expect that the pressure that you are calculating from this side, which is P1, and the pressure that you are calculating from the other side, which is P2, these two pressures, they have to be equal at this point. That means, when you are calculating from this side, continue to finding out pressure as a function of R, from this side solving this equation, for example, and then when you go to the other from the other side, you are having a pressure equation which is a function of R from this side. But here at this point, at the point of discontinuity, the two pressures have to be equal. So, P1 has to be equal to P2, that is important. And the second thing is that K1 del P1 del N, that means, this is basically negative of VR at this location. So, you are what you are doing here is you are at the surface of discontinuity, you are matching pressure and velocity. You are assuming that the pressure and velocity, they must be continuous. That means, from inside whatever velocity is there, from the outside also, if you come at that same point, the velocity have to be equal. One has to satisfy this conservation of one has to satisfy the continuity, right. Whatever flow is coming from this side and whatever flow is going into the other side, they have to be equal. There is no accumulation here. So, accordingly, this K1 del P1 del N has to be equal to K2 del P2 del N. N is what? N is normal to which is indicated by N. So, at this equation is satisfied at all points on the boundary. What is the boundary? Boundary where the strata, inside it is K1, permeability is K1, the outside the permeability is K2. So, at that boundary, the N is basically normal to this boundary. So, that means normal to this boundary. If I have an area and if I want to find out what is normal to it, then what we do here is we say that this is normal to it. Okay. So, similarly, here we have this N is normal to this boundary. So, basically it is K1 del P1 del R. Okay. So, that this is representing the radial velocity. So, velocity must be continuous and pressure must be continuous. So, this is one condition one has to, these are the two conditions one has to satisfy apart from these two governing equations. And the reason for such permeability variation, it could be this kind of discrete permeability variation is, one reason could be partial plugging. Partial plugging means something is being injected, for example, during at the time of drilling or at the time of at the time of fracturing, there are some fluids which contain some suspended matters. That fluid is entering into the pore space and plugging the pore space. So, obviously, the permeability will decrease at those locations. So, there could be partial plugging, or if one does acidizing as in artificial stimulation, then that means they inject acid to clean up the debris from the pores, so that the pores are more communicable. So, then that also will that will also increase the permeability. In partial plugging, the permeability is decreased, and here the permeability after stimulation it is increased. So, because of these reasons, there could be discrete change in permeability. So, now if we try to solve this equation, what we see here is, I have mentioned region 1 and region 2. So, we had a region 1 and we have a region 2. Region 1 has permeability K1 and region 2 has permeability K2. So, region 1 we have that it's a general equation that is valid there, P1 is equal to A1 ln R plus B1, because you remember we had the original equation that we derived there is P is equal to C1 ln R plus C2, right. So, that is the pressure profile. So, here in this case, instead of C1 and C2, we are putting these constants as A1 and B1 for region 1 with permeability K1, and for region 2 with permeability K2, we are writing it as A2 ln R plus B2. So, in this case, the constants are different, but finally, this if you solve grad square P is equal to 0, you will end up with this form of equation. P is equal to some constant multiplied by ln R plus some other constant. So, automatically you will have this equation there. If you solve this Laplace equation, you will end up with these two solutions for this solution applicable to P1 and P2 for the two regions. Now, boundary condition we have imposed is at R is equal to RW, that means R is equal to RW means at the well. So, this is the well, right. So, at R is equal to RW, RW is the radius of the well. So, there the pressure is PW. So, that has to be satisfied. PW is equal to A1 ln RW plus B1, and at R is equal to RE, RE is far away from this. So, let us say this radius is RE. So, at far away it is at R equal to RE, P is equal to PE. So, PW is coming in within the region of permeability K1. So, it is A1 ln RW plus B1, whereas PE is in the region of permeability K2. So, that is why it is A2 ln RE plus B2, and at the interface, let us say R is equal to R0. So, you are calling this interface as R is equal to R0. So, R0 is where this transition from permeability K1 to permeability K2 takes place. So, so at that interface R equal to R0, pressure from both sides have to be equal, we said, and the volumetric flux that is the velocity that has to be equal. So, when we apply that, we see here if pressure has to be equal, then A1 ln R0. So, simply P1 we are measuring now, instead of R we are writing it at R0. So, this is the pressure at R is equal to R0 from inside. So, from the inner region from region 1. So, this is pressure applicable from pressure from region 1 at R is equal to R0, at R is equal to R0, and this is pressure from region 2, this is pressure from region 2 at R is equal to R 0. So, these two they have to be equal, the pressure, the two pressures have to be equal, and at the interface the velocities are equal. So, what would be the velocity? It is minus k 1 by mu this quantity. Now, I can see here when I take a derivative of this del p del r. So, when I take del p 1 del r, obviously b 1 is constant. So, this is only a function of r. So, that is what is written. So, minus k 1 by mu del r of a 1 ln r at r is equal to r 0, and from this side the velocity would be minus k 2 by mu, that same thing. This time it is del r of a 2 ln r. So, that means this is essentially saying minus k 1 by mu del p del r. Now, del p, I should say del p 1 del r at r is equal to r 0 is equal to minus k 2 by mu, the region 2, del p 2 del r at r is equal to r 0. So, that is, so instead of del p 1 del r, when we take a derivative of this del p 1 del r, then obviously del b 1 del r is 0, and this we have to take the derivative of this. So, that is exactly what has been done here. So, now if we now try to see what kind of solution one gets. So, we had basically solution for discontinuous radial variation we are looking at. So, we have seen 4 equations. What are those 4 equations? We had seen 4 equations, and those 4 equations were one is this equation 1, equation 2, equation 3 and equation 4. We have these 4 equations, and we have 4 unknowns. What are those? A 1, B 1, A 2, B 2. So, these are the 4 unknowns and these are the 4 equations. So, now if we now look at the solution of these 4. So, we have solution for discontinuous radial variation, 4 equations and 4 unknowns. So, we get P 1 is equal to, this is the solution. I mean, I have I am not putting the providing the steps here that are required to arrive at this equation, but these are the 2 P 1 and P 2 that we have. So, now if you try to plot these equation P as a function of r, and if this is the point where r is equal to r 0. So, one can see that we said that from between r w, actually this must be r is equal to r w and this must be r is equal to r e. So, the between r w and r 0 you have one equation. So, you have one curve. Between r 0 and r e you have another curve. So, these two curves are different. Okay, there is a discontinuity I can see, but the pressure coming from this side and pressure coming from that side, they are meeting at the same place. Now, if we did not have a variation, if we you remember what did we see that time? We have seen this kind of a profile when the permeability was uniform, but now we have what? Now we have a discontinuity. That is what we are seeing, that this is the r is equal to r 0. So, there would be a discontinuity. Okay. Of course, this point starts at r equal to r w. So, essentially the right thing to do here would be to start from r is equal to r w, r below r w we are not talking about it, and the pressure at r equal to r w would be not 0, it would start from some finite point here. So, this curve should be this and followed by this, and if you have a uniform permeability, then it would be a continuous line. But if you have different permeability K1 and K2, then in that case there would be a discontinuity, but the pressure has to be equal at this point, the velocity has to be equal at this point. Okay. Velocity has to be equal at this point means the K1 mu is constant. So, K1 del P del R and K2 del P del R, they have to be same. So, you can see very well that if K1 is equal to K2, then del P1 del R has to be equal to del P1 del R has to be equal to del P2 del R. So, in that case there would be no, that the slope of this line at this point and the slope at this line of this line at this point, they would be equal. So, that means you will have a continuous line, which we have shown here. Whereas, since the permeabilities they are different, so that is why we have a discontinuity, and this discontinuity will be more pronounced the more there is a this K1 K2, if they are orders of magnitude different, you will see this discontinuity more pronounced. Anyway, when you have these pressure profiles in place, then one can write the equation here. Once again we are familiar with, first of all, minus K by mu del P del R, but since Q is rate of fluid flow from the reservoir to the well and VR is from the well to the reservoir. So, that means the sign is inverse. So, that is why this minus sign is dropped, because Q is defined that way, and Q is essentially flow rate, whereas the VR that we talk about, that is the volumetric flux, right. The superficial velocity is same as volumetric flux, and volumetric flux means volumetric flow rate divided by area. So, if you want to convert that to the volumetric flow rate, then you have to multiply this by the area. Now, area is what? Area is 2 pi r h, right. This height is h and 2 pi r. So, area of the cylinder is 2 pi r h, but they are not writing h here, because they have written reservoir to the well per unit sand thickness, that is important. So, per unit sand thickness means h is equal to 1. So, if you consider h to be 1, if you consider h to be not 1, h to have a finite value, put the h here, there will be a h continued. Okay. So, Q is equal to this quantity, and then now if you take this pressure profile and take the derivative of it, you end up with an expression of flow rate, which is given by this. So, if there is a break in permeability, one can have a way to solve this. I mean, this Laplace equation that we have discussed earlier for a single permeability setup, that Laplace equation has to be solved now. In this case, we have, last time we had only one equation, P is equal to C1 ln R plus C2, and our job was to find out what is C1 and what is C2 and plug them, and then write K minus K by mu del P del R and be happy with that as an expression for VR. But now, since we have two different permeabilities, so we have to solve this Laplace equation for the two domains, one with permeability K1 and another is for permeability K2, and they have to be coupled at the interface. At R is equal to R0, you have to assume the continuity in terms of pressure, the pressure from this side and pressure from that side has to be equal, and the velocity from this side and velocity from that side, this has to be equal. So, these velocities are equal and pressure are equal, putting these two conditions, you can get this flow rate. Okay. So, this is how the discontinuous radial variation, this is how this discontinuous radial variation is handled. Now, let us look at the situation where you have permeability. If a permeability variation is in a linear system, because we have been talking about cylindrical coordinate, of course, cylindrical coordinate has is more important when somebody is working with a reservoir or working with an electrode where some fluid is injected or fluid is collected. Many a times you will find in an electrode the fluid is collected from a particular location, and so that would be acting as a point sink, that would be acting as a sink. So, it is flow would be radially moving towards the sink. So, in those cases this kind of cylindrical geometry is perfectly is a perfect way of doing things. Now, it may so happen that you are simply working with a linear system in a particular setup, you are working with linear system. So, how these permeabilities they play out? So, linear system means that suppose I have a core, we have been talking about this core, right. So, suppose we have a core and we have let us say I am having a flow rate here and I have a permeability up to this point is the permeability is let us say K1 and permeability beyond this is K2. It is a linear system, not a cylindrical system, just a one dimensional problem, right. I mean, it could be we just used a cylindrical cross section, but we could have used a square cross section, that is fine. You can use a square cross section, it does not matter. And we could have used a square cross section as well. So, now this is suppose let us say I have a permeability K1 and permeability K2 and they are in series. So, now if somebody wants to know what is the effective permeability of this, that means why do I need to know effective permeability? Suppose I am having a flow rate Q and I want to know what would be the pressure drop in this case. So, how would I find out the pressure drop? I will use Darcy's law. So, Darcy's law means I need say for example, you can say that let us say this length is L, and let us say the pressure drop across this is delta P, I write it. Okay. So, we would write then Q is equal to or Q divided by area, let us say the cross sectional area is A. So, Q divided by A is equal to, then we have to write some permeability K divided by viscosity this, and delta P, let us say I write this delta P as P inlet minus P outlet. So, delta P is defined let us say as P inlet minus P outlet, to avoid any confusion about whether you have delta P should be taken as minus or plus. Let us say this is what is delta P. So, delta P divided by L. So, I can find out what is delta P. I mean, if I do not want to run this experiment as such, I may like to find out what would be the delta P I can expect if I inject certain flow rate of some say milliliter per minute or something. So, for this purpose you need a permeability. Had it been a single permeability setup, we could have used this equation, Darcy's law. We can use it to find out what is the delta P, but provided I am giving you a permeability let us say of 500 milli Darcy, that means 500 into 10 to the power minus 3 Darcy. 500 into 10 to the power minus 3 Darcy. So, this is 500 into minus 3 Darcy, let us say I give you this K. So, you can find out immediately what is the corresponding delta P, flow rate being known. Now, if you have a situation where you have K1 and K2, so should you be writing K as K1 plus K2, or what would be the right way of expressing K in terms of K1 and K2? So, we can think of this situation. Also, there could be a parallel situation where you have let us say a block, you have a block like this, and let us say I have a permeability which is existing here as the upper one has K1 and the lower one has K2. So, that means I have permeability of K1 and K2 which are running in parallel. One thing I must point out at this time is that running these two permeabilities parallelly and still expecting the flow to be unidirectional, that may not be that easy, because suppose there is a flow taking place and I am expecting that the flow will take place in parallel. That means, here I am having some velocity which depends on k1, here I am having some velocity which depends on k2. Okay. So, then one must ensure that there is no cross flow happening. So, one must ensure that these two permeabilities, they are somehow separated. Okay. These, particularly if the K1 and K2, they are varying by a large magnitude, by orders of magnitude, in that case you can expect that fluid will tend to channel through higher permeability region. So, one must have this separation in place, which may not be the case, or which is not the case for permeabilities in series. So, if you have such kind of sequence, then how do you find out what is the effective permeability? In this regard, I would in fact, I am going to close this discussion at this time, but before you come for the next lecture, before you attend the next lecture, I would suggest you review this, your theories of resistances in series. That means, you have two resistances in series. How do you find the effective or equivalent resistance in this case? And if you have the resistances in parallel, which is R1 and R2, and how do you find the equivalent resistance where the resistances, two resistances R1 and R2 are in parallel. So, let us just before, these are some fundamental concepts of electrical resistances. So, please review this this particular part before we start, and before we proceed further with this discussion. That is all I have as far as this lecture module, this part of the module is concerned. So, I will continue this discussion again in the next class, where we will talk about how to incorporate these understanding into the two permeabilities in series and two permeabilities in parallel. That is all I have for this particular module. Thank you.